Hi everyone, and thank you for being here. Today I'll be presenting our work on SD3.5-Flash, distribution guided distillation of generative flows. I'll walk you through how we address key limitations in traditional distillation frameworks, and our approach delivers a model that generates image in just a few steps, preserving both quality and prompt fidelity as confirmed by extensive human evaluation, and even runs on devices like the iPhone. Diffusion models have become state-of-the-art for image generation. They produce very high-quality outputs, but they are often slow and large. A single image may require up to 30 seconds of iterative denoising, even on powerful server GPUs. This makes them impractical for many real-time or consumer use cases. One promising solution is distillation. Instead of running hundreds of denoising steps, we can train a smaller student model to mimic the output of the original multi-step model. Recent works, such as distribution matching distillation, show that you can dramatically reduce the number of steps required while still maintaining strong image quality. At its core, DMD tries to align the distribution of a few-step student model with a multi-step teacher model. This is done using a scale divergence objective. In practice, the gradient of this objective boils down to comparing teacher and student scores on samples generated by the student. But here's the catch. To compute this objective, you need denoised endpoint estimates, and then you have to renoise them for score calculation. This process introduces noisy gradients, and that becomes especially problematic for rectified flow models where we typically rely on clean paired noise sample mappings. This limitation is what motivates our refinement. To address the noisy gradients problem in DMD, we introduce a technique called timestep sharing. The idea is simple. Instead of renoising endpoint estimates, we leverage intermediate time steps that are already produced during the multi-step denoising process. This allows us to compute the DMD objective directly without having to add random noise again. By removing that extra randomness, the gradients become much cleaner and more stable, which improves both the efficiency of training and quality of generated samples. Other than aesthetic quality, distilled models often show weaker prompt image alignment compared to their teacher models. To address this, we introduce something we call split-timestep fine-tuning. The idea is to divide the time steps into two ranges. Here we have 0 to 500 and from 500 to 1000, and train two separate branches on these intervals. By doing this, we effectively increase the model's capacity since each branch is specializing in a different part of the trajectory. After training, we fuse the two branches together during inference and interpolate their weights with a ratio that maximizes prompt alignment. Even after timestep distillation, our model is still very large. 8 billion parameters with everything, and that's too big to run comfortably on consumer devices. To make it practical, we apply quantization, specifically reducing the precision of the weights to 8 bits and even 6-bit format. On Apple hardware, we go further, rewriting key operations so that they map efficiently onto the Apple neural engine while still preserving numerical precision where it matters. This quantization step dramatically reduces the memory footprint and compute load. As a result, we can generate 512 pixel images in under 10 seconds directly on iPhones and iPads, something that was previously impossible with full precision models. Here you can see the latency numbers across devices, showing how much efficiency we gain by quantization. To really understand performance, we didn't just benchmark latency, we also conducted extensive human evaluation. We used an ELO rating system where models are compared head-to-head and scored based on user preferences. We find that our SD3.5-Flash models consistently outperform competitors across very different compute settings, from large server GPUs to laptops and even down to mobile phones. To wrap up the device story, let me show you something we think is really exciting. Here, we are running our distilled and quantized model directly on an iPhone with an A17 chip. This is a real-time demo at 512 pixel resolution with no speedups or time-lapse, exactly as it is running on the device. You can see that just within a few seconds, the phone is able to generate a high-quality image, in this case, a photo of a cat. This shows that with our approach, high-quality diffusion generation is no longer limited to server GPUs. It is practical and even on consumer hardware like phones. I will let the rest of the video play out so that you can see different images generated for different prompts. Okay, so moving on. Let's look at some qualitative comparisons. Here we show results across a range of prompts, comparing our 2-step and 4-step models against strong baselines like SanaSprint, NitroFusion, SDXL DMD2, and SDXL Lightning. We find that our model has better attention to detail. It can capture concepts like illustration of the cat on the textbook and the ostrich wearing the fedora without distortions, which we can see in the other competitors. Here we show more side-by-side qualitative comparisons. For the first prompt itself, our models do not have artifacts in the plushie or in the hand, which almost all of our competitors do. In the second row, you can see our models capture the slot's details and the van much more faithfully, while in the third row, there is much better realism and anatomy in generating people as well. In this page, we can see in the first row, other models are hallucinating, often adding a corgi in the living room or distortions in the painting, which our model doesn't. In the second row as well, we have better compositionality and do not add snow to the grass or distort the subject. Finally, for the last row, we do not add extra rope to the wooden toy horse, while the competitors generate horses which look like they're made of rope itself. We note that our model can also generate text much better than the competitors in the first row and have superior aesthetic appeal both for the painting and the ornate treasure chest in the last two rows. We conduct a user study based on image quality and prompt alignment with 124 annotators to evaluate images generated from 4 different seeds. For each generated sample, 3 users vote on 2 images from 2 different methods, rating them on visual quality and image prompt correlation. On the left, you see results for image quality. Our model consistently scores at the very top, outperforming SDXL DMD2, Lightning, HyperSD, and NitroFusion, and even exceeding the 50-step SD3.5 teacher. On the right, we measure prompt adherence, how well outputs align with a given text. Here too, our 4-step model performs on par with or better than leading baselines. That brings me to the end of this talk. To summarize, we showed how timestep distillation, split-timestep fine-tuning, and quantization together make it possible to run high-quality diffusion models in just a handful of steps and directly on consumer devices like laptops and phones. Thank you so much for your attention.